In this lecture, we're going to stop talking about acid dissociation constants. And we're going to look at what happens when we have a base that's in water and dissociating and how we characterize its strength. So we'll be looking at the base ionization constant or the base dissociation constant, whichever you prefer. So remember, base strength, just like acid strength, is really measured by how much our reactant base forms its conjugate acid. And so we're really going to be looking at the equilibrium between that base and conjugate acid and deciding what a strong or weak base is based on that. So like we did with acids, we're going to apply the same concepts here. So if our Kb, B for base dissociation, right, instead of Ka, if that's less than 1, we're going to call this a weak base because it'll favor reactants. And if that Kb is larger than 1, we'll call this a strong base because it's going to favor our products. And like we have acid dissociation constant or acid ionization constant, here we'll have base ionization constant, or again, base dissociation constant, depending on what book you read and, who your teacher was when you had intro chem. So I flip between the two all the time, unfortunately. So remember that when we had a larger Ka, it meant a stronger acid. So with Kb, it's going to be the same. A larger Kb is going to correspond to a stronger base. And we're going to calculate that Kb expression by just using our equilibrium constant expression. And it's for this base dissociation reaction where we have a base plus water. It's going to form hydroxide plus the conjugate acid of the base. That conjugate acid and hydroxide concentrations are going to be multiplied on the numerator of our expression. And on the denominator, we'll have the concentration of the base. And these are all concentrations at equilibrium. Here's some examples. Let's just look at a couple. We have the carbonate ion and aniline. And for these, we can see we have Kb's. The first one is 1.8 times 10 to the negative fourth, which is larger than our second one of 3.9 times 10 to the negative 10. And so I'm going to say that our carbonate ion is the stronger base because it has a stronger Kb. Let's look at an example and walk through it. So we're going to calculate the Kb, or the base ionization constant, for the reaction below. And we're just being told it's ammonium's dissociation. We know some of the equilibrium concentrations for the conjugate acid and base, and that they're going to be 0.003 molar, and that the base itself will have a concentration of 0.5 molar. So let's write out our dissociation reaction and then our Kb expression and plug those values in. So NH3 is our base. We'll add that to some water, H2O, so it's an base dissociation reaction. It'll be in equilibrium. Remember, we're going to have one of those hydrogens are going to be donated from our acid, which is water, to our base, which is ammonium. And we'll end up with NH4 plus OH minus. So writing out an equilibrium constant expression for this, Kb, is going to be equal to the concentration of our hydroxide ion times the concentration of our ammonium ion, all divided by that ammonia concentration. Now I'm leaving out water, right? Because this is going to be a pure liquid and it's not going to be aqueous. And so it falls into those heterogeneous equilibria kind of category. So it's going to be ignored. Or it would be equal to 1, or you can call it just negligible. So let's go ahead and plug in the values that are given to us. Again, we have 0.003. That's for the conjugate acid and the conjugate base. And we have 0.05 for the base. So our base is at NH3, and our conjugate acid and conjugate base are the products of this base dissociation reaction. So it's that NH4 and OH minus. So that means our Kb is going to be equal to that 0.003 times 0.003 molar divided by 0.5 molar. which will give me a value that is 1.8 times 10 to the negative fifth. So that's my Kb value. And it's a weak acid. It's smaller than 1. So it's going to favor reactants, which makes sense because we're told that that has the higher concentration already. So that should kind of confirm our expectations.